Welcome guys. Here's yet another question here. As you can see here, this question requires some knowledge of complex numbers besides just algebra. Go ahead and solve it if you really understood it. You can check the last minute for the answers. Solving time. So let's understand the key terms and underline them before we actually start solving them. So we have roots, which basically means the zeros or the values of x which satisfy the equation given here. This is our equation. And these roots are the vertices of a polygon. So basically, each root is represented as one vertex on the Gaussian plane. We will explore what that is later. So each root happens to be represented as one vertex on this Gaussian plane. So since it's mentioned polygon, we don't really know how many vertices it has, nor do we know how many roots it has, therefore. So we have to find the complex area as well, along with the number of roots over here. We need to know the roots, then use the area formula, and we'll get the answer. So here's how it works. So our Gaussian plane looks like this. So this is the imaginary axis, which represents the imaginary part of the numbers, and this is the real axis, which represents the real part of the numbers. Let's say we have a complex number, x plus iy, and x is the real part. So its x coordinate will be x, and its y coordinate will be the coefficient of I. So this is y, this is x. And this is the point x plus I, y. Let's take a look at what I is now. So I is basically the imaginary root of -1. It does not necessarily exist, but it's necessary to solve this problem. So I into root of x plus 1 by x equals x plus 1 by x. So x plus 1 by x is kind of scary to deal with, so let's take x plus 1 by x as p. So here we get I into root of p equals p. Let's square on both sides. You get I squared, which is -1, so minus root p squared gives us p, because the square and the root cancel each other, and p squared is p squared. That's it. Don't cancel p, because if you do, you'll get only one solution, or you'll only get half the number of roots which actually exist. Not necessarily exist, but basically you'll get only half the roots of this question, because some of the roots could be imaginary or complex. So let's transpose p on to this side. We get p squared plus p equals 0. Factorize this out. We get p into p plus 1 equals 0. So that means p has to be either 0 or -1, because p plus 1 has to be 0 or p has to be 0. And if p plus 1 has to be 0, p has to be -1. That's the zero product rule. If the product of any two polynomials or numbers is 0, then at least one of them have to be 0. So here's how we do it. Our p was x plus 1 by x. This one. Yeah. So x plus 1 by x equals 0. That's our first equation. And x plus 1 by x equals -1. So if we transpose the -1 inside, you get plus 1 equals 0. That's our second equation. Working with the first equation now, we get, let's multiply both sides with x. We get x squared plus 1 equals 0. That means x squared equals -1. So x has to be either I or minus I, because minus I squared also happens to be -1. Every perfect square or square has two square roots. One is the positive square root, which we usually use while dealing with problems, and the other is the negative root, which we usually don't bother about. So if we multiply this thing by x on both sides, we get x squared plus, we'll take 1 first, and then we'll go with 1 by x, because 1 has a higher degree. So 1 into x is x, plus 1 by x into x is 1, equals 0. Now, this is actually a very interesting equation. Let's explore why. So you probably know only one cube root of 1, that is 1, but there actually happen to be two other cousins of the same family which share the same relationship. That is, cube them and you get 1. So if you take this one, this side, you get x cubed minus 1 equals 0. Then factor this out because this is the difference of two cubes. You get x minus 1 into x squared plus 1 squared. We'll write 1 squared here, which is basically 1. And in the middle, we'll write their product, x into 1. So we get x equals 0. And by the zero product rule, either x minus 1 or x squared plus x plus 1 equals 0. And if x minus 1 is 0, x equals 1. And yeah, that's the familiar cube root we know about. Now, solving this equation, we get two roots, which also satisfy this equation, x cubed equals 1. And by using the quadratic equation formula, minus b plus or minus root b squared minus 4ac by 2a, where our a is going to be 1. Ignore this equation, okay? So our coefficient of x squared, which is a, is 1. Our x coefficient is b, which is also 1. And our c is also 1, the constant over here. So minus b means minus 1 plus or minus root 1 squared, which is 1, minus 4 into 1 into 1, which is 4, by 2 into 1, which is 2. This gives us two roots. Omega is the symbol, which is minus 1 plus, we'll take the divided by 2 separately. So minus 1 by 2 plus root 3i by 2. And we get omega squared as well, which is minus 1 by 2 minus root 3i by 2. Basically, omega's conjugate. So basically, a conjugate is when you have two complex numbers. If one complex number adds up to the other complex number and the sum is real, and also if their product is real, then the complex numbers are conjugates of each other. It kind of works like surds, which has a similar formula and conjugate business. So those are the roots of the equation. We have I minus I and omega squared. Let's write them down here. I minus I omega and omega squared. So this is the formula for the complex area of a polygon on the Gaussian plane, and it is equal to I, which is the imaginary unit, root of -1 by 2 into the sum of matrices of two vertices of a polygon taken at a time. So we have matrix of x1, y1, x2, y2 plus matrix of x2, y2, x3, y3, and so on until the matrix of xn, yn, x1, y1, where n is the number of vertices we have in this polygon. But as you can see here, if we substitute these values into the formula, we notice that it's going to become difficult and complicating because we have many fractions, negative signs, and roots. So it makes it very complicating. So as you can see here, these four roots form a trapezoid over here. That is because two distinct points on the Gaussian plane and their respective conjugates always form an isosceles trapezoid. So we can take advantage of this fact and use this formula instead, which is much simpler. So it says that the complex area of a trapezoid on the Gaussian plane is equal to I into h by 2 into a plus b, where h is the height or the difference between the x coordinates of omega and I over here. There's also the difference of x coordinates of omega squared and -I. Then we have a, which is the length of the shorter side, the distance from omega and omega squared, which is also the difference in their y coordinates, and b is the length of the longer side, which is the distance between I and minus I, which also happens to be the difference of their y coordinates. So let's plug these values into this formula and see what we get. I hope it works. So this is the arrangement we have left. We have the four roots on the Gaussian plane with their respective coordinates. And now, yeah, this is the formula we have for the complex area of a trapezoid. And by making the necessary arrangements, we can substitute it into this formula and get the answer. So this is the formula we have now, because since we know the shape, we can use this formula. So unless you know the shape of the polygon, you better use the formula discussed earlier in the video, which is about the complex area of a polygon, which is something to do with matrices and all that. So now let's make the necessary arrangements. So here we have I into h by 2. So our h would be the difference of the x coordinates of omega and I, which is 0 minus negative half, which is half. Our a would be the length of the shorter side, which is the distance between omega and omega squared, or the difference of their y coordinates, which is root 3 by 2 minus negative root 3 by 2, which is root 3 by 2 plus root 3 by 2, which is root 3. And b is the length of the longer side, which is the distance between I and minus I, and it is equal to 1 minus negative 1, which is 1 plus 1, which is 2. So let's substitute these values into this formula. So we have I into 1 by 2 into a plus b, which is root 3 plus 2. So now we have I by 4 into root 3 plus 2, which gives us, using distributive property, we get root 3I by 4 plus I by 2 square units. So this is the area of the quadrilateral we had. So this is the solution, the area of the roots of the equation given earlier, and I hope you enjoyed this video. Thanks for watching, and for more videos, subscribe to my channel, and please do like this video if you enjoyed it. Stay tuned for the next video. Until then, see you soon. Goodbye.